All right, now let's keep discussing the oscillator. There's a few more things that we should discuss. We've spoken about frequency and how it's related to pitch. Now, we should also talk about the fundamental frequency and harmonics, because these are a very big part of what makes the timbre, the overall sonic character of the sound that's generated by our oscillator. So, going back to the grid. As I mentioned before, we're starting off with a triangle oscillator. This generates a triangle waveform, and this is a bit brighter than what we would get from something like a sine wave. Now, I mentioned before, different waveforms, if they have different shapes, they're going to generate different tones. I'm going to right-click here, and I'm going to replace this triangle oscillator with a sine wave. All right, what we see here, these are different waveforms, and some of these have different ways to change and manipulate the waveform. We'll start with the sine. Now, when I bring out the sine wave, let me also reset the skew parameter. So looking at the oscilloscope here, we can see, all right, right off the bat, I have a waveform, and we have this smooth curve downward. We go up smoothly. I have a smooth curve here. There's no sharp, jagged edges, all right? Looks nice and round. If we play a sound with this, let's get a sense for how this sounds compared to the triangle that we listened to before. All right, has a much more pure tone, sounds much more smooth. I don't hear a lot of bright tones to it. And there's a specific reason for this, all right? Before I get into that though, what I'd like to do is instead of looking at this through an oscilloscope, I wanna use a spectrum analyzer. Using a spectrum analyzer will allow us to see all the frequencies being generated by the sound within the range of human hearing, from 20 hertz to 20,000 hertz. So if I go back up here to my display area, there is a spectrum module. Now, one thing I should make clear, if we're looking at the oscilloscope here, we can see, even though I'm not playing any sound, I still see a waveform being generated. Now, the reason why is because, even though I don't hear anything, the reason I don't hear anything is because this oscillator is connected to a volume envelope. The volume envelope is only triggered when a note is received, and I'm not playing a note. However, the oscilloscope is not connected to the volume envelope. It's connected directly to the output of the oscillator. So this is not listening or waiting for a volume envelope. It's just showing me the output of the oscillator. That's fine. But for the spectrum analyzer, what I'm going to do is connect this after the volume envelope, which means that we're not going to see anything in this display until we've actually played a note. Let me expand this. Here's the output of my volume envelope, and I will connect this here, and we'll be able to see these side by side. Now, the main difference between the oscilloscope, here I'm able to see the waveform and the wave cycles. Here in the spectrum analyzer, I'm going to see a range of frequencies, and I'll see where this particular sound falls within these range of frequencies. So let me play a note. Okay. If I hover my mouse where this peak is, in the corner here, it's going to tell me the frequency and the volume for this particular peak. This is about 118 hertz. Now, what I notice is that above this, I don't really see anything else, all right? So there's not a lot of high frequency content here. All I'm really hearing is this tone. We can refer to this as the fundamental frequency. As I play a note, the sine wave is oscillating at a specific frequency that corresponds to this pitch. I don't hear any other higher, brighter frequencies being generated. All I hear is this fundamental frequency, all right? Now, let's say that I start to change or alter the shape of the waveform. We know that by altering the shape of the waveform, that's going to affect the timbre, the sonic characteristics of the sound. But why does it affect the timbre? Well, let's see. I'm going to adjust this skew parameter, which is going to change the shape of the sine wave. And I didn't do too much, but already I can see, looks like there's a lot of high frequency content that's being added here that wasn't there before. All right, it's that much brighter. And as I look at the waveform here, I see I don't have the same smooth changes, the smooth rises and falls that I had before. We're starting to get something that looks a bit more angular, all right? And then as I play it, I get more high frequency content. So what's actually happening here? These peaks that are being added after my fundamental frequency, we can refer to these as harmonics, all right? These harmonics, there's a certain mathematical ratio from the fundamental frequency. As these different harmonics get added, they add harmonic content to our sound, higher frequency harmonic content. These frequencies sound natural. They're in consonance with the fundamental frequency, which means they don't clash. It fits together well. And that's why we don't notice any sort of weird warbling or anything like that. It just sounds like the sound gets brighter. There's more high frequencies added to it. So when you're dealing with an oscillator and you're trying to figure out what sort of sound that you want to generate or start with, we know that a sine wave is going to sound very pure and very smooth because a sine wave doesn't really generate any upper harmonics. It's just that fundamental frequency, the frequency related to the pitch that we're actually hearing. If we want something brighter, we can go with something that's a bit sharper, more angular, because those waveforms generally generate more harmonics, which give us that much more high frequency content to work with. So, knowing that, this gives you a way to take an oscillator and either start with a specific waveform or be able to manipulate a certain waveform to get the exact sonic characteristics that you want.